So picking up back with fluid deficit or dehydration. When we have a fluid deficit, it's usually it can have a few different causes. One of the major ones is insufficient body fluid intake. So we don't have enough intake. It also can be caused by excessive loss, either through sweating, diarrhea, vomiting, so there's an imbalance, or both. One of the ways we can measure it is through changes in body weight. If we have an accurate body weight before it happened, we can figure out how much they are dehydrated afterwards. Dehydration is much more serious in infants and older adults. Water loss can also be accompanied by other electrolytes and protein loss, such as with diarrhea or vomiting. So we can lose the water and the electrolytes. So some causes of dehydration: vomiting, diarrhea, like we just said, excessive sweating due to overexertion, and this will also cause a loss of sodium levels and cause sodium to be lost at the same time as water. Diabetic ketoacidosis, and this is where it's lost through the urine, through diabetes, where it's excessive urination, and the fluid, electrolytes, and glucose pulls the water out through the urine, so we have more urination. In older adults and unconscious people, we have insufficient water intake. This is especially because the thirst mechanism is not quite as strong in older adults, so it's very important to monitor fluid intake. Another risk factor is the use of concentrated formula in infants. So that formula is made to a certain percentage of water. What can happen is somebody thinks, oh, my baby's not getting enough food, we need to give them some extra nutrients, so they concentrate the formula too much and don't follow directions, and then this can cause dehydration in infants. Okay, so some of the effects of dehydration include dry mucous membranes, such as the mouth and tongue, dry. Decreased skin turgor or elasticity. So if you pinch the skin, it doesn't go back to its normal state. It actually stays elevated. The blood pressure can drop, weaken pulse, and also fatigue. All are symptoms of dehydration. It can also be, and especially older adults, decreased mental function, confusion, and loss of consciousness. Some manifestations of dehydration. Again, manifestations are things that we can see. Decreased skin turgor, dry mucous membranes, sunken eyes, where the eyes become sunken fontanelles in infants, which is the soft spot, rapid low blood pressure. Less water means less blood, which means less blood pressure. The hematocrit can increase because they have less water, less plasma, and so there's going to be a higher percentage of cells. The temperature can increase, and decreasing levels of consciousness. So over time, as dehydration effects kick in. Also, urine low output can be low, and have a high specific gravity or concentration. So here we can see a comparison of edema and dehydration. So what we see is fluid excess with edema, and dehydration is a fluid deficit. Some of the differences are key is the swelling of the skin, weight gain, the blood pressure increases, and edema, where it would decrease in dehydration, lethargy in both of them, fatigue and weakness, and with edema, it really depends on where is the edema occurring at. And if it's like in the lungs, it can cause pulmonary congestion, cough, and rails. And let's look at the laboratory values right quick. So With edema, we see the decreased hematocrit, and with dehydration, we see increased hematocrit. When we see decreased sodium levels with edema and increased electrolytes, well, it's really variable depending on the cause of dehydration. And then the urine is low specific gravity, high volume. With edema, is going to have more urination, and then dehydration is going to have less urination, high specific gravity. So how do we try to compensate for fluid loss? Well, one is by increasing thirst, and that's going to increase the water intake. Another is increasing the heart rate because there's less blood flow, so we increase the rate of the heart. We can have constriction of the cutaneous blood vessels, which are the ones that go to the skin, so we have more blood flow going to the core. We produce less urine, and we concentrate our urine more. This next type of fluid compartment disorder is called third spacing of fluid. The fluid shifts out of the blood into a body cavity, or into a tissue, and it can no longer re-enter the vascular compartment or the blood vessels. So the fluid has shifted out of the blood vessels into a compartment. This is different than edema because the edema is inside those tissues in the interstitial fluid. This is where it's more into a body cavity. So it's third spacing. That's what it's called, where it's going out of the body, out of the tissue. One of the ways this typically can happen is through burns. Burn victims often have the cells have a lot of damage, and due to the release of the proteins and things of that nature, and this causes a high osmotic pressure in the interstitial fluid. So the water will leave out of the capillaries into the interstitial fluid, and then it will evaporate, and it cannot go back in. This is called a third spacing of fluid. Also, in some other cases, when there's a great increase of capillary permeability due to some infections, it can go into these compartments, and that's third spacing. Okay. The last thing we're going to kind of cover is the electrolytes. This is a good place to go back and review your notes from where they're at, maybe Anatomy 1, Anatomy 2, because this is building on it. What is a cation and anion? Maybe your chemistry class. Cations are positive and anions are negative. You need to kind of know where they're more concentrated at. Whether they're intracellular inside the cell or extracellular outside of the cell. So if we look, we can see that sodium and potassiums are opposites of each other. Sodium is more prevalent in extracellular fluid, which is the blood, and it's less in the intracellular. And then potassium is more prevalent in the intracellular. Calcium is variable on the intracellular, and then it's a small amount in the extracellular. And then magnesium is more in the intracellular. So magnesium and potassium are more intracellular. Sodium and calcium are more extracellular overall. The anions, or the negative ions, are bicarbonate, chloride, and phosphate. Bicarbonate is a buffering ion, and it's more in the extracellular compartments, such as in the blood. And then chloride is also more extracellular, and phosphate is more of an intracellular anion. Okay. So sodium imbalance. So just a quick review of sodium. There is a chart on Moodle that goes into more details about all the different effects and characteristics, along with the cause and effect and characteristics. So if we see that sodium is primarily a cation in the extracellular compartment, and it's extracellular fluid, and it diffuses between vascular and interstitial fluids. So it goes in between the blood and the interstitial fluid in between the cells. And it diffuses between those two. And it is transported into and out of the cells by the sodium-potassium pump. And it's actively secreted into a lot of secretions such as mucus and things like sweat and other secretions. It exists in both the form of sodium chloride, table salt, and sodium bicarbonate. And it is ingested through foods and beverages. And like I said, you really need to go and look at that chart. It goes into more detail about what is when we have high levels of sodium and low levels of sodium, and what does it cause. So please go and look at that chart. Our next review of potassium. This is the major intercellular cation. Serum levels are actually low with a very narrow range. It's ingested in the foods. It's excreted through the urine. Okay. Insulin promotes the movement of potassium into the cells. It does have a small, is influenced by acids and bases. Excess potassium ions in the interstitial fluids causes hyperkalemia. Okay, and hyperkalemia is where we have too much. Hyper means above normal. Abnormal potassium levels are life-threatening because they can affect cardiac conduction and the beating of the atrial ventricles. The review of calcium. Calcium is an important extracellular ion again, and it's more prevalent extracellular. It's ingested in the food. It's stored in the bones, and when we have low calcium, it can be released from the bones. It's excreted in the urine and the feces. It is controlled by two hormones, the parathyroid hormone and calcitonin hormones, and those are antagonistic hormones that work opposite of each other, and they promote the absorption and secretion from the bones. Vitamin D promotes calcium absorption, and that's why our milk is fortified with vitamin D, so we can absorb the calcium that's actually in the milk. Vitamin D it can be ingested or synthesized in the skin. So if you go outside each day, it can help synthesize vitamin D and help you to absorb your calcium, and it's activated in the kidneys. Magnesium imbalances. Magnesium is primarily an intracellular ion. There's two. If you have low magnesium, it's called hypermagnesium, and magnesemia, and it results from usually malabsorption, the inability to absorb the magnesium, or malnutrition, not getting enough in our food. It can be associated with alcoholism, and it also can be caused by the use of diuretics, which are water pills that cause getting rid of more urine, diabetic ketoacidosis, hyperthyroidism, and hypoaldosteronism. All of these diuretics, diabetic ketoacidosis, hyperthyroidism, and hypoaldosteronism, all of them are going to cause excess urination and cause a loss of the magnesium. However, magnesemia can occur from renal failure because we cannot get rid of the magnesium, so it causes a buildup, and this can cause a depression of the neuromuscular functions and the reflexes. Phosphate imbalances. So phosphate is for bone and tooth mineralization. So it's important for our bones. Our bones are made up of calcium phosphates, actually. It's important also for our metabolism. We use phosphates to make the phosphate on our ATPs. This also has a small role in acid-base balance, and it has an integral role in the cell membrane. If you remember back, we call them phospholipids. The phosphate is in a reciprocal relationship with calcium, so if calcium's high, then phosphate's low. So they're opposites of each other, so it's more of an intracellular intracellular cation. I'm sorry. Hypophosphatemia is where we have low phosphate, and this usually comes from malabsorption, not getting in our diet, and also diarrhea or excessive antacids. Can reduce the phosphate because antacids have a lot of calcium, and calcium is opposite of phosphate. And then hyperphosphatemia is where we can get rid of the phosphate, and due to and it has high phosphate, and it's usually cut from renal failure. Okay. Chloride imbalance. Chloride is the major extracellular anion or negatively charged ion. Chlorine and sodium go together, sodium chloride, so they're related to each other. Chloride and bicarbonate can shift in response to acid-base imbalances. So chlorine follows the bicarbonate, bicarbonate kind of follows the chlorine. They can shift in response to keep the balance. So if one goes in, the other one goes out, and they shift with each other. Hypochloremia is low chloride levels, and this is usually associated with alkalosis, which is where we have a high pH. The pH gets really high, and it causes the chlorine to shift, and it can cause the hypochloremia. Also, the early stages of vomiting, because we lose the hydrochloric acid, we lose the acid, and that's going to cause the chlorine to move. Hyperchloremia is excessive chlorine, and it's usually from excessive table salt intake, sodium chloride intake. As we can see here is our pH scale, and we're looking at the blood. The normal range is between 7.35 and 7.45. As we move away from normal, which is 7.4, we become acidic or basic. And if it's in an acidic state, we call that acidosis. And if it's in a basic state, we call that alkalosis. Okay? And if we move too far away, both of them can cause death. Okay. The control of the serum pH. So we have what's called buffers in our blood that help with pH changes immediately. We can also use the respiratory system and the kidneys to affect our pH levels. So the respiratory system alters carbonic acid levels, and it changes the pH, and then the kidneys modify the excretion of the acids and absorption of bicarbonate ions, and that helps regulate pH. Respiratory is very temporarily. The kidneys is more significant, and it's a slower mechanism, so it's more long term. Here's a really good image that shows changes in acids, bicarbonate, and serum pH. So if we start here at number 1, we can see the cells cellular metabolism produces acids. Okay, and the acid is in the blood. Okay, and then what we can see is the blood has carbon dioxide and water, and that produces carbonic acid. Okay, it's carbonic acid. Okay, the acid, the hydrogen ions, binds to the bicarbonate here, and it can be carried to the kidneys. Okay, and then the kidneys can process that carbonic acid, reabsorb the bicarbonate, and get rid of the acid. Okay, the blood has less hydrogen ions and more bicarbonate ions. This is bicarbonate because it's negative. Okay, it can pick up the acids and go out and become the carbonic acid. It can pick up the acids. Okay, and that means there's left bicarbonate, left buffer. It goes to the lungs where we get rid of the CO2 and the water. We can get rid of the carbonic acid by getting rid of the CO2. Now we have less carbonic acid, and it continues to process. So the kidneys get rid of the actual H+. The lungs get rid of carbonic acid. Okay, they're both going to increase pH. Okay, but the kidneys actually can lower it long term. There's also a couple other buffering systems such as the phosphate hemoglobin protein buffering system. So let's see the sodium bicarbonate carbonic acid system. It typically runs 1 carbonic acid to 20 bicarbonate ions. So that's typically what we see. So we have 1 carbonic acid to every 20 bicarbonate ions. And if we get rid of one of the carbonic acids, then we go and we shift over one of the bicarbonates over to the carbonic acid. So now we have 1 carbonic acid and 19 bicarbonate ions. And then we can switch them back and forth to keep the buffer, because those bicarbonate ions can pick up hydrogen ions and reduce the pH, or increase the pH. It's controlled by the respiratory system in the kidneys. We'll go into this more later. And also lactic acid can decrease the bicarbonate levels because the acidity is picked up by the bicarbonate. So we can compensate in our body for a pH imbalance. So if the pH gets too acidic or too basic, we can compensate. It's usually limited and is short term. This does not remove the cause of the imbalance. It only allows us to compensate for it. And this is done by changing the balance of hydrogen ions and bicarbonates in the system. So we move them back and forth. The concentrations is temporary. We can change the respiration and the renal function. Okay? We can only do this so long. If the levels get so out of whack, then we get a condition called decompensation. This is where the problem becomes more severe, and we're unable to compensate anymore. So one of the things we see, like for if our blood is very acidic, acidosis, what we'll do is we'll breathe really fast to get rid of the CO2, and this will bring our pH back up because it works with the bicarbonate. So we breathe fast and we compensate. But as long as the pH continues to lower and get more and more acidic, then we can't breathe fast enough to get rid of the CO2. Then eventually we have decompensation, and this is life-threatening because we cannot maintain homeostasis. So acidosis is where we have excess hydrogen ions and low pH. Alkalosis is we have a deficit of hydrogen ions and a higher pH.